Hello everyone and welcome to my explanation of the neuromuscular junction. So let's first give a brief definition of neuromuscular transmission and then dive into details and explain exactly how this process happens. Neuromuscular transmission is the process by which a motor neuron stimulates a skeletal muscle. Just to give you some orientation about this diagram, what I've drawn here is the presynaptic membrane, and this is the postsynaptic membrane of the skeletal muscle, and the area in between is the synaptic cleft. So what happens exactly is that we have those action potentials traveling and moving down the axon carrying the depolarization wave, which is about positive 30 millivolts. Once it reaches this area here called the axon terminal, it stimulates very specific channels here called calcium, voltage-gated calcium channels. Those are voltage-gated calcium channels. They are stimulated by this positive 30 millivolts when the action potentials reaches to the nerve terminal. Once stimulated, those channels allow for calcium ions to get into the axon terminal. So calcium ions getting inside. So calcium has a very important role here. It allows for those synaptic vesicles here, those contain acetylcholine. It allows those vesicles to fuse with the presynaptic membrane in something that looks like this. So it allows acetylcholine to get outside the synaptic vesicles. Once acetylcholine ions exit the nerve terminal, they go and bind to those receptors on the sarcolemma of the skeletal muscle, and those receptors are very specific and they are called nicotinic receptors. So the nicotinic receptors are present on the sarcolemma here, and this, by the way, is the postsynaptic membrane. So once it binds here, it allows for those channels to open, and by the way, those channels have a very specific name. They're called ligand-gated sodium channels. They allow for sodium ions to get inside the cell. Sodium ions are positive and they bring a positive wave into the cell. The membrane potential normally here is about negative 90 millivolts. So once we get those positive charges inside the cell, we take it to about negative 55 millivolts, which is the threshold potential. Once we reach negative 55 millivolts, we trigger an action potential. What happens in an action potential is that those specific channels here called voltage-gated sodium channels start to open and make sodium ions to enter the cell in huge numbers. So sodium gets in the cell, bringing those positive charges inside the cell, a lot of positive charges. So remember, we were at about negative 55 millivolts, which is the threshold potential. Now we might reach up to positive 30 millivolts. And this process is called depolarization. So once the inside of the cell is depolarized, this depolarization wave travels along this structure here in the cell, and this structure is called the T-tubule. Just to give some orientation, this is the T-tubule right here, and this structure is called the sarcoplasmic reticulum. And the sarcoplasmic reticulum is a calcium storage center. So what happens exactly is that this depolarization wave, once it arrives here to this place, it triggers this specific receptor, and it's called dihydropyridine. Dihydropyridine receptor binds to this portion here of this receptor, and this one is called ryanodine. it sort of pulls it back and opens this gate. Let me just, oh no. It opens this gate, allowing for calcium ions to move outside the sarcoplasmic reticulum, and we're going to see where those calcium ions go right now. Calcium ions travel and go to this structure here in the cell. It is called the sarcomere. Sarcomere is the functional unit of the muscle cell. So we said that calcium ions exit the sarcoplasmic reticulum, goes and binds to this receptor in this specific protein. This protein has a specific name. It is called troponin. Just to give you some orientation on this diagram as well, the thin filament in red here is called myosin. Let me write it down. This thick filament, it is called myosin. And the other one, the other thin filament, is called, let me write down thin filament as well, thin filament actin. It is called actin. We can also see this structure here in green, and this structure is called tropomyosin. It is another protein. The tropomyosin blocks the the myosin heads from binding to those actin filaments. So what calcium does specifically here is that once it binds to those troponin heads, it allows the unblockage of this protein, which is tropomyosin. It sort of takes it out in this way, like this. So it opens up and it allows those heads, those myosin heads, to bind to the actin filaments, moving them backwards and then generating muscle movements. This is exactly how muscle contraction happens. There's also one more thing to mention here, is that once we reach positive 30 millivolts after the depolarization happened, we want to take the cell back to its resting membrane potential, which was negative 90 millivolts. So how exactly does this happen? We have another type of voltage gated channels here. This one's called voltage gated potassium channels. Those potassium channels are activated once we hit positive 30 millivolts, and they allow potassium ions to move outside the cell once stimulated. Of course, potassium ions are positively charged, so once they leave the cell, they make the outside of the cell more positive, and they make the inside of the cell more negative. They leave behind negative charges, a lot of negative charges. So those negative charges take us from negative 90, positive 30 millivolts to about negative 90 millivolts, which is the resting membrane potential. It might take it to even more than that. It could reach to negative 100, negative 110, and so on. This allows for hyperpolarization of the cell. And that was it. Thank you so much for listening.